All right, it's 8:30. Let's go ahead and get started. All right, good morning, everybody. How's everyone doing today? An hour earlier than we're used to, so it's really early in the morning. So I know it's tough. This whole week's gonna be tough because of the daylight saving. I guess on the bright side, we have more daylight in the evening. Okay, so today, of course, the first day after the midterm. So of course, I don't have the midterms ready just yet. But I plan to grade them over the next 2 days, so I will have them for you guys on Thursday. Okay. So for those of you on Zoom, I should have the midterm graded by Thursday. So if you want to come to the lecture, pick them up. You can do so. If you can't make it to class this week, I'll still have them in my office. And so after Thursday, if you come to my office at any time, you can pick up your exam then too. Okay. I really have not looked at them yet, or have not touched them, so I have no idea kind of what to expect. But that's going to happen after that. I think today's a good time to mention kind of the grading policy that I have in this class. So usually what I do, so I don't curve the exams in kind of the traditional sense, but at the end of the course, what I'll do is I will scale the group. So once all the grades are in, so all the homework grades, all the midterm exam grades, all the final exam grades, once all that's in, then we'll have like an overall class average grade. So what I like to do is that if that class average grade is below, usually I like to scale it up to about 77%. So let's say the class average grade is about 75, 76%. Then what I'll do is I'll add 3 percentage points to everyone's grades until the average is up to that. Okay. So that'll happen at the very end. And so I know after a certain exam, there's always questions of are you going to scale this exam? So I don't scale the individual exams, but I will scale at the very end. That's just to make sure that our average is kind of where it is. And I think when you curve grades according to when I was in college, most of my professors did like top 10% get A's, the next 40% get B's or whatever. So I don't do that. That's way too complicated for my taste. And so I just look at the overall average and I just add points and so. But again, I have no idea what the average is, but last time I taught this was 4 years ago, and the average on the first midterm was around 70%, about 35 out of 50. So I expect it to be fairly similar to this week. We'll kind of see where it is. Okay. Okay. So another announcement I have to make. So homework 4 was just posted yesterday. So homework 4 is it covers basically everything we're doing with vector calculus, right? It's going to cover mostly today's lecture and the next 2 lectures, and it's going to be due the Sunday before spring break. Okay. So I don't want you guys working on anything over spring break. So that's why I'm having it due on the Sunday before. That way, you guys can turn it in. You guys can enjoy your spring break, and then we'll come back and do Fourier analysis for when we come back. Okay. But that should be due next Sunday. Okay. Not this upcoming Sunday, the following. Okay. All right. So beside that, the plan for today is we're going to continue on talking about vector calculus. Specifically today, we're talking about differential vector calculus. So we're talking about things like gradients, divergence, and curl. Okay, so that's the plan for today. We should be able to finish that up today, and then Thursday we'll start talking about integral vector calculus. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? All right, so let's go ahead and get started. Today we're talking about differential vector calculus. Okay. And so when I say differential vector calculus, what I mean by that is all derivative operations. So I think, everyone's familiar with the concept of a derivative. I mean, we've been working with differential equations in this class. Okay? Once you kind of step up to multiple dimensions and multiple, variables, these derivative operations kind of take on a different flavor. Okay, so they become a little bit more complex. And so it's a lot more complicated when you have multiple variables, multiple dimensions than just taking a simple derivative. Excuse me. And so there's several operations that we're going to cover today. So the first operation that we're going to cover is the gradient. So we'll actually be spending a majority of the time talking about the gradient, because the gradient is used a lot in engineering. From there, we'll talk about the divergence, what that means. Finally, we'll end today talking about the curve. So probably these are terms or these are operators that you may have seen before in previous classes. Maybe a physics class, or maybe I know some of you have taken fluid mechanics already, so you might have seen some of these in like the Navier-Stokes equations. Okay. I remember when I first saw a lot of these operations, I think I was first introduced to them in my physics classes. I had no idea what they meant. The professor just kind of put those operations on the board in this very long, complicated equation. And we were expected to kind of know what they meant, but it didn't. Okay. And so just kind of like what I mentioned last week. So today, and kind of just in this section of the course in general, we'll learn how to compute these, of course. But I think what's more important is to get kind of more of a physical intuition in terms of what these actually mean. Why are they significant for engineering, and how do we actually interpret them physically? Okay. And I'll give some examples of how you can kind of interpret them. Using examples like heat transfer fluid mechanics and even topology. And so I want you guys to keep that focus in. So it's learning how to compute these, yes, it's important, but having their physical intuition is I think more important, because in reality, when you see a differential equation or when you see a vector equation with these operations, most of the time you're not actually going to be computing that by hand. But what's more important is that when you do see these in an applied setting in another class, you kind of understand what they mean, so that you have kind of a deeper understanding of the governing equation. It's okay. So let's start with the gradient. And so the gradient is kind of the first, thing that we should learn. And so it kind of takes the concept of a derivative and kind of expands it to multiple variables. Because up to this point, when we think of a function, especially our differential equations that we just finished covering, those equations are only functions of a single variable, right? And so when you take the derivative, there's really only one variable that you can take the derivative of, which is that single variable. Okay. But now we're dealing with fields, right? And so when you have a field, you have a function of multiple variables. Right? And so, for example, let's think of a three-dimensional field. So one example of a three-dimensional field would be a function of x, y, and z. Okay. And so, just kind of spitballing here, let's say we have 2y cubed plus 4xz plus 3x. Okay. Right. So you can see this field has multiple variables. So it has x, y, and z. Okay. And because we have multiple variables, that means we can take a derivative in each of those variables. But now, since we have, a function like this, when we take a derivative of just one of the variables, we call that a partial derivative. Yeah, partial. Yeah. And so when you take the partial derivative of a function, you take the derivative of that variable. So, in this example, we're taking derivative with respect to x, and we're treating all other variables as constants. Okay. All right, so let me do this kind of slowly just so you can kind of see partial x. And I'm going to do it for each individual term here, right? So remember, derivative is a linear operator, and so we can kind of break apart whenever you have a plus or minus sign into separate terms. The partial x of 2y cubed plus x e plus partial x of 3. Right. So let's carry out all these partial derivatives. Okay? So first we have partial x of 2y cubed, right? So there's no x in this expression. And so even though there's a y is one of our variables in this field, but it's not x, right? And so just for all intents and purposes, when we take the derivative with respect to x, this just goes away, okay? So even though y is a variable, but when we take the derivative with respect to x, we treat it like a constant. Okay? Right. Then we have the derivative of 4xz. And so when we take the derivative of this, we focus just on the x term here. Okay, so I know there's a z in there, but remember we're treating that z as a constant. And so when we take the derivative of x, the derivative of x just by itself is just 1. Okay, and then we're going to carry through those constants. And so we're going to have 4z. And then that last term is easy. We have partial x of 3x. We know the derivative of that is just going to be partial f, partial x, 2, 4z plus 1. So this right here is a partial derivative with respect to. Have you guys seen partial derivatives before? I think probably 258, right? Okay, so you guys are familiar with the concept. All right, and so we can do the same thing. So partial f, partial y, partial f, partial z. Okay, so we can take the derivatives of all three of our variables. So partial f, partial y, partial f, partial z. Okay. And so we have our three partial derivatives, right? So we have, a function of three variables. And so we can take, what that basically means is we can take a derivative in each of those three variables. What the gradient does is the gradient takes all those partial derivatives and kind of puts them all into one place. Okay. And so it looks like this. So the gradient, and so the way that we denote it is we have this kind of upside down triangle. The gradient of f is equal to partial f x partial f y f equals z. Okay. Or if you want to put it in IJK notation, it would look like this: partial f x I hat plus partial f I j hat plus partial f z. We're basically taking the derivative of a function in every single direction and then putting that into a vector. Okay. Of course, this assumes that F here is a scalar field. And so it's a multivariable function, but it's scalar valued, and so F itself is just one value. Okay. But notice what we did here. So we took a scalar field, we took F, which only has one value at X, Y, and Z, and then we turned it into a vector. Okay, so this is an important property of this gradient. And so when you take the gradient of a scalar field, you take the gradient of a scalar field, you end up with a vector. Okay, so you increase the dimensionality by one. Okay. And that trend applies too. So you can actually take the gradient of a vector field as well. And when you take the gradient of a vector field, you end up with a matrix. Okay. Gradient basically increases the dimensionality of your function by one. Okay. Go from a scalar to a vector to a matrix to a four-dimensional or three-dimensional tensor. It gets crazy after in the weeds of structural mechanics. You can keep basically taking repeated gradient operations. You got a four-dimensional matrix. So I know 4D chess is like a meme, but there actually is four-dimensional objects in applied math. Yeah, as for how to actually draw that, I have no idea, but that's why I'm into fluids. I'm not into structural mechanics. Okay. One last piece of trivia, in case no one's told you before. This upside down triangle here, the name for this is actually a nav. That's just some trivia. You can go through all of, you can go get a PhD and never know that that's called. So, but in case you're wondering. All right, any questions on this so far? Okay, so that's the gradient. And so let's do an example. So let's take the scalar field that I have above and compute the gradient. All right, so to do this, we need all the partial derivatives. And so we've already taken the partial derivative with respect to x. The partial f, partial x is 4z plus 3. Partial f, partial y. This is 6y squared. Partial f, partial z is equal to 4. And so if we take the gradient of f, we're just going to take all these partial derivatives. So we get 4z plus 3, 6y squared. Very straightforward. So if you have the functional form of the field that you're working with, you just have to take its partial derivatives to get the gradient. Okay? And of course, this is in 3 dimensions, but we can also have 2D fields as well. And so if you have 2D fields, then your gradient is just two components. Okay. All right. That's a gradient. The gradient has a lot of really interesting and cool uses in applied math and engineering. Okay. So we're going to talk about two. two main uses for the gradient and their physical interpretations. So the first is called the directional derivative. And two, we're going to talk about the direction of maximum increase. Okay. So let's start with the directional derivative. Okay. And so when you have a multivariable function, when you have a field function, right? Their function can vary in all different directions, right? And so it's different than a one-dimensional function where your variations can only occur in that one direction. And so this is reflected in the fact that in all of our partial derivatives, right? So partial f, partial x, that will be the variation of your function f in the x direction. Partial f, partial y will be the variation in the y direction. And partial f, partial z, if you have a three-dimensional field, is the variation in the z direction. Okay. And when I say variation, what I mean is rate of change. So I use the term variation. It's a bad habit of mine, but what I mean is basically rate of change. Okay. And so the way that you can interpret that is that if you have your field or your multivariable function and you walk in the x direction or you walk in the y direction, the partial derivative is kind of the change that you're going to experience. Okay. And so I think the easiest kind of analogy or the most kind of illustrative analogy that I can think of is a topology map. Right? So remember we talked about last Tuesday, a topology map shows the relative heights in a certain area. Or kind of the little egg yolk in the middle of that plot. That might be the highest point on the hill or the highest point of the mountain. Okay. And as you walk down the hill, each of those contours is going to show the different. And so, if you were to start, at the very top of the mountain, if you were to walk in the x direction, the change in height that you would experience, or how steep the mountain is going to be, is given exactly by partial f, partial x. So that's great, so the partial derivatives kind of give us the rate of change of our function in each of the cardinal directions. Okay? But what if we want to take the rate of change in an arbitrary direction, right? So maybe we don't want to walk down the mountain in the x direction. We want to walk down the mountain in this direction. We want to walk down the mountain in that. We want to know, how steep is the mountain going to be if we walk in those directions. is that possible for us to do, from the gradient? Okay. Of course, it's possible. Otherwise, I would not bring it up. And so the way that we do that is we take the directional derivative. Okay. And so let's say that the direction. So you want to find the rate of change in a certain direction, and we represent that direction with a vector. And so let's say that this vector, let's say we want to find the derivative in that direction. And we'll call it the vector A. Okay. And so A is represented by A1, A2, A. So we'll assume that's in three dimensions. Okay. And so to find the rate of change of your field in the A direction, all you have to do is take the dot product between the gradient of your function f and the unit vector that points in that direction. And so we can represent it like this. And so, notation wise, what I like to do is I do partial f, partial a vector. Okay. So this is the directional derivative of f in that a direction, okay, is equal to 1 over the magnitude of a. So we're going to take the magnitude of a and divide it by a. Okay. So this is just to ensure that our direction here is a unit vector. And then we're going to take the dot product with the gradient. So first thing you do is that if you have your direction, divide by its magnitude to get the unit vector, and then take the dot product with the f. All right, so let's do a quick example just to see how this is computed. Okay. And so if we have a multivariable function, so let's say we have a field of x, y, and z given by 2x squared plus 3y squared plus z squared. You want to find the rate of change of f this direction. We have 1, 0. Okay. So in other words, we want to take the directional derivative of f in the 1, 0, minus 2. Okay. So let's go ahead and plug into our directional derivative. First, we have the gradient of f. And so we're going to take the partial derivative of f in each of the directions. We have partial f, partial x. Partial f, partial x is going to be 4x. Partial f, partial y is going to be 6y. And partial f, partial z is 2z. Now we need to find the unit vector that points in the a direction. So we're going to take the magnitude of our directional vector. And so we're going to use our distance formula here. So we have 1 squared plus 0 squared plus 2 squared over the square root. And so that's going to give us square root of 5. Okay. All right, so we plug this in. So we have partial f a equal to 1 over root 5 times our directional vector. So 1, 0, 2. Dot product here. For the radian, 4x, 6y, 2. Okay, so let's go ahead and carry out that dot product. So the 1 over root 5, that's just a scalar multiple. So we can just kind of keep that out in front so we don't have to worry about that. We have 1 over root 5 times 4x times 1 plus 6y times 0 minus 2 times 2z. And so we carry this out. What we get is 1 over root 5 times 4x minus 4. This is partial f. All right, any questions on how we obtained this this result here? Okay. All right. So one thing you'll notice, and you may have noticed this already when we've taken the gradients, is that when we take these partial derivatives, we still obtain functional expressions, right? And so the gradient or the partial derivative of function is not just a constant. Okay. And you can see that here as well. And so when we take the rate of change of f in the a direction, we still get a function of x and z. And so what this tells us is that, you know, the rate of change of f is still itself a function of x and z. And so this also changes depending on which location that you're in. And so intuitively that makes sense too, right? And so if you're standing up on top of the hill, right? The hill is going to be steeper at some parts than the others, right? So depending on whether you're at the top or maybe you're kind of halfway down the hill, maybe you're on the other side of the hill, right? The steepness is going to change because, you know, the hill is not, you know, built uniform. Okay. And so what we can do is say, you know, maybe, you know, we have this rate of change here, but maybe we want to evaluate that rate of change at a particular location. So let's say for this example, let's evaluate this rate of change at the point 2, 1, 2. Okay. And so let's go ahead and plug in for that. So partial f, partial a, at 2, 1, 3 equal to 1 over root 5 times 4 times x, and so our x in this case is 2 minus 4z, so 4 times 3. Okay. All right, and so with the root 5 underneath, we end up kind of with a nasty number here. And so if we plug this into a calculator, we end up with minus 1 over 7, minus 1.78. All right, and so we get a number here. after, and this is kind of true in general. So after you do a bunch of calculations, you go through kind of a long process like this, you end up with a number, it's kind of easy to forget what that number represents. So, especially, I think, especially in vector calculus, it's important to kind of step back. Whenever you finish a problem, think about, okay, what exactly does this number represent? Or what exactly does this result represent? And so this minus 1.789, what this represents is the rate of change of that in the A direction. And so A in this case was 1, 0, minus 2 direction. Evaluate it at the point P. Okay. Right, so you're standing on a hill. I guess in this case, it's a 3-dimensional hill. And you want to find the steepness of the hill in a certain direction. And then if you're standing on a certain point of the hill, you want to find its exact steepness in that direction. And that's kind of what this represents. All right, any questions on this result here? Okay. All right, so that's the directional derivative. And so that's kind of one cool application of the gradient. Okay, so the gradient, lets you find the rate of change in basically any direction you want. Okay. Now let's talk about the next application. So this one I think is actually more relevant for engineering, and that's the direction of maximum increase. Okay. And so, recall from earlier today that, when you take the gradient of a scalar field, you end up with a vector, right? So the gradient of a scalar field is a vector. We haven't really talked about what that vector actually represents. So, kind of up to this point, that vector, its only purpose is just to hold our partial derivative, right? But that vector itself, or the direction of the gradient, actually is very significant. And so this vector that the gradient produces actually points in a very significant direction. Okay? And that direction is the direction of maximum increase, just like the title indicates. And so in other words, if you were to take the gradient of a scalar field and you were to take the unit vector in that direction, so you find the magnitude, you divide by it, that direction that is pointing in, that's the direction of maximum increase. Okay. So let's go back to our hill analogy, right? And so let's say that you're standing at the bottom of the hill and you want to find, what's the direction of steepest increase, right? So let's say that, you really want to get a good workout and you want to run up the steepest part of the hill, right? And for some weird reason, let's say that you have a functional representation of the height of the hill, right? So you have the topology function for some weird reason. And so if you want to get the best workout, you would take the gradient of that topology function, you'd find that direction, okay, that the gradient points at, and you just run up that direction. Okay, so this is pretty significant because a lot of engineering equations and a lot of engineering physics actually depend on this thing. All right, so let's go over a few examples. So let's do a heat transfer example. So I don't think many people are in the heat transfer course, okay? But it's okay. You know, I will tell you right now, you don't need to take heat transfer. I will tell you everything that you need to know about heat transfer in one sentence. Okay. The heat transfer professors won't like this. Okay. But when you talk about heat transfer, heat likes to go from hot stuff to cool stuff. That's literally all of heat transfer. You don't need to take the course anymore. So that's all you need to know. Dr. Banks is gonna kill me. So let me do an example here. And so let's say that we have a rectangular plate, okay, and we represent the temperature of this plate as a field function. Okay, so we have temperature, it's a function of x and y. And let's say that we have, this plate is heated in such a way that the left-hand side is hotter than the right. Okay. We have a hot side and a cool side. And so if we follow the fundamental law of heat transfer, trademarked by myself, okay, then we know that heat or energy is going to flow from the hot to the cool side, right? And so heat will go this way. If we represent this with a field function, we get the same thing. Okay, so let's say that the left-hand side of the plate is held at a constant temperature of 75 degrees C. And then as we go from left to right, the temperature is going to vary down to 50. Then we have 70. 65. 60. And so with these numbers, you could say our temperature field here, T of X and Y, is equal to minus 25 X plus 75. So that's the temperature field that that follows this kind of. We can take the gradient of T. Okay. And so if we take the gradient of this function right here, we're taking the partial derivatives with respect to X and Y. Okay. And so in this case, our gradient of T, we're going to take the partial derivative of T with respect to X, and so we have minus 25. Okay. And we take the partial derivative of Y, or T with respect to Y, we end up with 0. Because there's no Y dependence there. So let's plot this. Okay. So up here, we have the temperature field T of X and Y. Let's plot the gradient field. Okay, where I'm going to represent each the gradient is going to be an arrow. And so this is going to be the plot of gradient of T. All right, so the nice thing about this gradient field is that it's a constant, and so it's a constant minus 25, 0. Okay? And so everywhere, we're going to have that curve. And so the gradient doesn't vary. So the gradient is always the same all throughout. Okay. So that's the gradient field. So the gradient field is always kind of pointing to the left, okay? Because that's the direction of maximum increase, right? And so the our temperature field is increasing from right to left, and so it makes sense that our gradient points in that direction as well. It points from right to. So we can make use of this information. So we can make use of this gradient, and we can make use of the fact that we know heat is going to go from hot to cold. Right? So heat is actually going to go in the opposite direction of this. And so while the gradient points in the direction of temperature increase, right, the heat is going to go actually in the direction of temperature decrease. Okay, and so we put this in functional form. And so we use the variable Q. So little q there is usually meant to represent heat transfer rates. Okay. And so it's a rate at which energy moves from one location to another. Okay. We can say this is equal to minus K times the gradient of T. Okay. For K, K there is a thermal conductivity of the material. And so, as you know, some materials are better at conducting heat than others. Okay. Usually when you have a coffee mug, it's made of some kind of ceramic, so you don't burn your hands, right? So ceramic has a pretty low thermal conductivity. Okay. You don't see very many copper or aluminum coffee mugs because you will literally burn your hand trying to, or I should say, there's a lot more hipster aluminum coffee mugs nowadays. So they look nice when they're sitting in your kitchen. They're just not very practical when you actually put and drink something out of it. But anyway, you can see from this equation here that, we have our gradient, right? And more importantly, we have this negative sign. Okay? And so what that's telling us is that, when we take the opposite of the gradient, so we take the minus direction of the gradient, that's the direction that heat is going to go, right? And that's exactly what we see here. And so heat is going in the opposite direction of temperature increase. In other words, heat goes in that direction of temperature decrease. Right. So this equation right here, I didn't just make that up. So this equation actually is one of the fundamental equations of heat transfer. And so this right here is Fourier's law. Right, so that should be one of the that's one of the first equations that you'll learn in the heat transfer course. So if you're taking it right now, you probably have seen this equation already. You probably should have seen it, 2 months ago. Okay. But if you're taking it next year, here's kind of a sneak preview of it. Okay. So there you go, heat transfer in a nutshell. Now you don't need to take the class because now you understand everything. Okay. I haven't taught heat transfer in a couple of years, but maybe this is why they don't want me to teach it anymore, because I say this on the first day, and then and then that's that. So maybe that's why they don't let me teach it. Okay, any questions on this? All right, and so you'll see, of course, we spent a decent amount of time talking about a heat transfer example, but you see this kind of concept of of the gradient in a lot of other areas of engineering as well. So let's talk about fluid mechanics. They haven't let me teach fluids in like 3 years too. Maybe this is the reason why. And so the fluid mechanics makes use of the gradient as well. Okay. But instead of temperature, we're talking about the gradient of pressure. And so for a fluid, one important property in the fluid is its pressure, right? So the pressure is basically the force divided by area that's exerted by the fluid. Okay. And so you have an internal flow, you have a pipe, right? That pipe, inside that pipe is fluid pressure. Okay. Fluid will flow. So fluid always, so very similar to heat. Fluid is going to flow from areas of high pressure to low pressure. And so we have the velocity u. This is about equal to minus the gradient of p. A little more complicated than that. And so, we have the full Navier-Stokes equation. And so, that of course is not shown here. And so we have just that. But in general, if you have a, high differences in pressure, then your fluid is going to flow in that direction. Okay? And so you see this the most in internal flow. And so flow that goes through a building, right? Usually the fluid is highly pressurized at some point by a pump, and that's what drives the flow out to your sink. Okay. But you also see this in atmospheric or environmental science as well. And so, I think that's particularly relevant. We're supposed to have a huge storm today. Okay. And so the wind that blows the clouds, the wind that blows the rain and stuff over to certain areas, that's caused by large differences in pressure in the environment. And so even in fluid mechanics, we make use of this gradient concept of, just knowing what direction is the maximum increase. And by token of that, we can take the negative sign and find the direction of maximum decrease. We can find out a lot about this. Okay. And so that's a gradient. And so the gradient has a lot of really interesting applications. I'd say those two, the directional derivative and the direction of maximum increase, I think is probably the most relevant for engineering. Now let's talk about kind of the other two operators that we talked about today. So let's start with the divergence. So the divergence, notice here that we're taking a divergence of a vector field. Okay? And so that's kind of an important distinction. So for a gradient, we started with a scalar field, basically a single valued function. Right? Now we're taking the divergence of a vector field. So remember, a vector field is it's multivariable and it's multi-value. Okay. And so just like we talked about last week, a vector is something that has components, right? So it's not only just one value, we have X, Y, and Z, okay, in 3 dimensions. But when we talk about a vector field, each of those components depends on X, Y, and Z. Okay, so each value of the function depends on all the variables. And so in the general sense, we have vector V, okay, where this V here is a vector field. So this vector V is going to be a function of X, Y, and Z. Okay. The way that we usually represent this is we have our 3 components, Vx, Vy, Ez. And each of these components are a function of X, Y, and Z. So Vx of X, Y, Z, Vy of X, Y, and Z, Z of X, y. All right, so the most common application you'll see for this is in fluid mechanics, and so when you talk about the velocity components of a flow field, each of those components is going to vary in x, y. The vector fields are quite complicated, and most of the time, most people do not like working with them because they're quite complicated. But the good news is that a lot of times when you do see vector fields in practice, a lot of times you'll see the divergence kind of right alongside. And so the divergence will take a vector field and turn it into a scalar field through a derivative operation. So mathematically, it looks like this. So we take our nabla operator, so we take the upside down triangle, okay, and we're going to take the dot product between that and our vector v. All right. And so when we do that, we're going to take basically the partial derivatives of each of the components of the vector v, and then add them together. So we have partial Vx plus partial Vy plus partial Vz partial Z. And so you take each component of the vector field, you take its respective partial derivative, then you add them up together. Okay. So let's do a very quick example. I'm going to show you how this is done. Okay. Let's say that we have a vector field. The vector field is given by 3xz, 2xy, and minus yz squared. Okay. So let's take the divergence of this. Okay. So the divergence of the vector field v, we're going to take each component and take its respective partial derivatives. We're going to take partial x of the first component, so partial x of 3xz plus partial y 2xy plus partial z of minus yz squared. And in the end, basically through that dot product operation, we end up with a scalar field. We have 3z plus 2x minus 2y. Okay. All right. Any questions on this? All right. So the divergence, you know, I won't go too much into it right now, just because its context is kind of more. You'll see a lot more of the context when we start talking about integral calculus, you know, starting on Thursday. So, you know, I won't say too much more here. Okay. But I will say that, you know, where you see the divergence a lot is in fluid mechanics. And the divergence is often used to represent things like conservation of mass. Right, and so depending on the value of the divergence, it'll tell you whether mass is being conserved, whether you have a source, or whether you have a sink. Okay? Because basically what the divergence basically tells you is it basically tells you if your vector field is kind of growing in magnitude in a certain region. Right, and so that will tell you basically if you have being observed or. Okay. All right, so I won't say anything more about the divergence. So when we go over integral calculus and we go over the Gauss theorem, we'll see the divergence again. So we'll kind of save it for. Okay, any questions on this? Okay, so the last 15 minutes today, I want to talk about the curl. Okay. All right, and so the curl of a vector field makes use of the cross product. Okay, so remember the last thing that we covered last Tuesday was how to take the cross product between two vectors. Okay, and so the curl of a vector field is basically the cross product between our nabla and our vector field. It looks like this. We have our nabla operator crossed with vector field V. And just like we learned last week, the way that we're going to compute this is through kind of a pseudo matrix determinant. Okay. We have I hat, J hat, K hat. Okay. And then we have the components of each of our input vectors. So, in this case, we have one special input vector, which is the nabla. So that's going to be partial x, partial y, partial z. And then the last row of the matrix is going to be our components of our vector field. This is going to be dx, dy, and bc. Okay, so let's go ahead and take the determinant of this matrix. And so if we do so, we get partial vz x minus, partial vz, partial y, partial vy, partial z, minus partial vz, partial x, minus partial vx, z, j hat, plus partial vy, partial x, minus partial vx, partial. But the equation itself is pretty complicated. So, that's why I think it's a little bit easier to remember kind of the cross product matrix determinant. But if you actually carry it out, then you actually end up with that expression. Okay. This one's about to right. Just kind of follow the matrix of terminations and that, that equation. All right. And so the most important thing, or one thing that a common thing that will that I'm that we'll hopefully get from today, is to think about what do we get from the output of this, right? And so when we think about our gradient increases our dimensionality. So if we take the gradient of a scalar, we get a vector. The divergence reduces our dimensionality. So you take the divergence of a vector, you get a scalar. And so the curl, you take the curl of a vector field, you get a vector field. Okay. And so we keep the dimensionality. If you take the curl of a vector field, you get a vector field. Okay. All right, so we're almost out of time today. So I want to make sure that I talk about the physical intuition. I do have an example in the notes that shows how to actually compute this, and so you can always check out the lecture notes online. Okay, but I did want to talk about what its physical representation is. And so just like the name implies, the curl of a vector field basically tells you how much that vector field has a tendency to swirl in a local region. So as an example, and so let's say that we have the kind of the simplest kind of spinning vector field that there is. Let's say that we have a spinning rigid object. Okay. Right, so I think kind of the most physical example of this would be like a vinyl, right? So if you have a spinning CD or spinning vinyl, right, that's a spinning rigid object. So let's say that this object is round like this, it's rotating or spinning with an angular velocity omega. It's rotating in the clockwise direction. Okay. And so the velocity field, if you were to write out the components of the velocity at every location on this turntable, you would get minus omega y, omega x, 0. So that would be the components of the velocity if you were standing at certain locations of the turntable. Okay. So it depends on two things. It depends on your distance from the center, and it depends on the angular velocity of the object. Okay, so we can take the curl of this velocity field. So we can take cross product of the nabla and the vector. Right, so this one's actually quite simple to compute. So you can actually plug this into the equation up here. And the fact that there's no z component, so vz is 0, and the fact that nothing depends on z, most of the components of the curl are going to cancel out. And what we end up with is 0, 0, 2 omega. And so our curl in this direction points in the z direction. So the direction of the curl is really significant because if you think about it, if you have a rotating object kind of flat on your table, right? The z direction is going to point vertically upwards. Okay? And so that's something that's important for the curl. So the curl is always going to point in the direction of the axis of rotation. Another thing that you'll notice from this result here is that our curl is non-zero, right? And so this means that if you are on this turntable, you are going to spin. Seem obvious, right? So yeah, obviously, you sit on a rotating object, you're going to spin. Okay? But more importantly, not only is your whole body going to spin, but your orientation is going to spin as well. And so I always like to think of it like this. So if you have, an object, and I think the simplest objects to do this with is like a simple like stick, like a twig, okay? And so if you take a twig, okay, and you sit it on the turntable, you sit it on the spinning object, okay? And so let's say the twig starts with an orientation like that, okay? So it's kind of pointing vertically. As the object rotates, and so as the whole entire object rotates from here to here, right? You can imagine that twig, which is initially vertically upwards, as it rotates to kind of the bottom of the rigid object, its orientation is going to change. So instead of being vertically upwards, it's going to be horizontal, right? And then that's going to keep changing. So as we go to this part, that twig is going to start to look like that. When we go up, it's going to be horizontal again, okay? And so on and so forth. Okay? And so the curl basically shows you this. And so the fact that the curl is non-zero means that your orientation is going to change. Okay? The opposite of this is when the curl is zero. And so when you have a vector field where the curl is zero, then we say that that field is irrotation. Okay. And so the opposite is going to occur. And so an object in an irrotational vector field is not going to change orientation. One very kind of quick example. So let's say that we have a flowing fluid field. Okay. And so let's say that the flowing fluid field looks like this. Right. So let's say that this is like a river or a stream or something like that. Okay. And let's say that for this field here, we have a curl of zero. Okay. Okay. So that means if you take an object here, okay, so let's take our humble twig, just like before, okay? And so as this twig kind of flows with the field, it's going to displace, right? And so its position is going to change as you go through the field. But the fact that the curl is zero means that its orientation is not going to change. And so when you kind of, you take a snapshot of the twig here, maybe wait a couple seconds, the twig is kind of downstream a little bit, okay? Wait a couple more seconds, it's kind of over here. Maybe it's over here. Okay. And so even though the position of this twig is changing, so it's kind of flowing with the fluid field, it's still maintaining the same orientation. So it itself is not rotating. Okay. And so that's basically what it means to be irrotational. So be irrotational means that your position might change within the vector field, but you yourself are not rotating. Okay. All right. Any final questions on this? Okay. All right. So that's all I got for today. And so that is all of derivative vector calculus. And so when we come back on Thursday, we'll talk about integral vectors. All right. So thank you guys for coming today. I know today was especially early since daylight saving, so I appreciate you. I hope you guys enjoy the rest of your day, and I will see you on Thursday.
Have a good day, Professor.
Thanks, you too. Zoom people, any final questions? Calvin and Elaine? Okay, all right, I'll see you guys Thursday then.